really difficult thing to really try to understand is that the difference between it's actually the answer versus it's getting close to that answer. So even though we say the limit as x approaches 2 over here, we say that it's 1.2 because that's what it's approaching. But it's that b that I kind of drew as a visual example, it's not at that spot. It's getting close. It's getting so close to a point where we're like, you know what? It's close enough. That's what it's going to be. It's like when we round off and stuff, right? We round off just close enough. And so that's what this arbitrarily close to means. And this is a very important definition, as I show you examples later, why this wording, arbitrarily close, is so important. So we want to take x sufficiently close to c. So we'll talk more about what that means. It's just basically we want to choose numbers closer and closer. Just in the first generic examples, we're going to go as basic as possible, then we'll talk about like this, what this arbitrarily close, sufficiently close is. Okay. For a later practice, I kind of showed you guys a little bit something like the limit of f of x as x approaches c is r. That's what this is over here, except I changed the word limit to r. Okay, so for you guys, just take a little moment, right? See if you can write this little example here. What is the limit of g of x as x approaches 5 is 10? Can you write what this limit is? Just a little brief teaser. It says the limit of g of x as x is approaching 5 is 10. If you wrote this down, limit as x approaches 5, g of x, 10. That's how we write our limit. So this is now in the notation language. So when we see this, we see that sentence we saw on the previous slide. Okay, we're converting that sentence into this notation so that it's just easier. So instead of us writing sentences all the time, we don't need to do that. Okay, notation's okay? If I'm going a little quick, you guys need me to repeat at certain points, just let me know. I tend to get carried away and distracted at times. So this is where we're going to start talking about what you think things are. I'm not going to actually tell you like what the answer is until a little bit later. So I just want to hear like some thoughts for like, what do you think? Okay. Let's look at A. This is your graph. Take 1 minute and think about, for A, when x is approaching 2, x is approaching 2 right here, what do you think the limit is?
Wait,
Take 1 minute and talk to your neighbors what you think it is.
if it's approaching from the left, the limit is 2. If it's approaching from the right, the limit is 3. That's why I'm saying if it approaches from the left, the limit is 2.
No,
if
they're
it
both
approaches
approaching
from the
at
right, it's 3.
They're both approaching negative and 3.
So it's 2 and 3. No, it can be either.
Because that's where they start, right?
Dude, we were literally taught this.
Any thoughts? Any guesses? Tiffany?
I would say 3 because the dot is solid.
3 because the dot is solid.
Yeah.
Laura?
I would say there's not a limit like overall, but like if you approach it from the left side, then it's the lower one that's open. But if you approach it from the right side, it's 3.
But that was. Okay. approaching from the left, it's what?
2. If it approaches
So
from
we
the right,
have
it's 3.
our logical reasoning, 3
That's what I said.
because it's not filled. And you guys are all guessing right now, and Lauren, you're saying that you would say none, right? Unless, that's interesting what you said. So you said if the limit is approaching from the left, then you're saying it'll go to 2. If the limit is coming from the right, you're saying it's gonna go to 3.
Oh, four times the limit.
Okay.
Or just before.
2.
Wait, is the limit where it equals 3 though?
Remember, we're not going to equal. Right? We want to get close to.
Like, I feel like the closest.
Oh.
I feel like the closest that it could get to 3 would be at y equals 3, since that's a closed point, not a. I don't know. They're
But
the same.
you're not trying to get exactly on.
They're
three.
literally the same
You're
thing.
trying to get close to 3, not exactly onto 3.
So they're both work.
But
So
3 doesn't.
that's why like the key phrasing is so important, right? This one has no limit. But then that's the thing though, right? When we start changing our wordings, what is this limit going to be? Like what are we going to talk about with this? Because functions typically break when you talk about piecewise functions. But that's the argument I'm trying to have build up in you guys, is that like we're getting close. We're not getting on the point. So the dots are irrelevant actually. And that's the big thing to really like juggle between, because we're really used to defining the point. And you're not wrong. A lot of math tries to define everything. Like there's even a definition for why division by 0 doesn't work and a proof on it. So there's all these things that we want to
The cookie
define.
monster can't share
this
little
side.
cookies with their friends.
Okay.
So you'll have no friends.
B. Let's
And
say my
you'll be
limit is
sad.
going to x is approaching 2, which is this asymptote.
Oh, infinity.
What do you guys think the limit is gonna be?
No limit.
Would it be the same logic that no limit?
Or, I mean, negative infinity,
Oh,
positive infinity.
there is a limit.
Isn't it 0? It's like.
So
The limit is 0.
these two are really, really good examples to show you that there's no limit.
Yeah.
Not the way we defined it, at least on slide 2. So one thing you can think about is that if there is a break, right, your function broke, there's no limit. Okay. But there are exceptions to the rule. So we're gonna look at the next slide that Lauren already introduced. There are cited limits. So typically speaking, when you have a function, right? When we talk about a limit as a whole, you're talking about having 2 b's on both sides, and you want to bring them close to wherever you want. And they both have to approach the same thing for a limit to count. But as you saw in the previous slide, that doesn't always happen, right? So we have another definition for this. We call these one-sided limits. The one-sided limits are written practically the same way as regular limits, except there's one more added bonus to it. So for this one, it says the limit of f of x as x approaches c from the left. What we're gonna do is that on top right of c, we're gonna put a minus sign to symbolize it's coming from the left.
Yeah.
And this time it will spit out a limit. It will definitely spit out a limit. Okay? Now, if I was saying that, okay, this is coming from the left, what about right? What do you think I'm gonna put up here?
Positive.
Positive.
You learn this.
Positive is coming from the right.
No.
So this one's from the right. This
You
one is
learn
left.
this.
Okay. So it's just depending, like, is this just telling you direction? Where are you coming from? Right? Are you coming from the left, or are you coming from the right on the graph? I probably should have done reverse when I said that, because you guys are seeing it differently. Okay, so I think you guys got the idea of how to write. We're gonna skip how to write on the next part. But let's go back onto the previous example.
Doesn't teach us good?
So, almost spot on, actually. If you look at A, and I'm coming from the left, that means my bead, the idea of that bead is coming from the left side, and I'm just bringing it as close to as possible. And eventually, what is it going to hit eventually?
I'm gonna take it over.
It's going to hit that hole eventually, right?
Hit it top, dude. No.
So because it's almost there, we're gonna call it, so the limit as x is approaching 2 from the left, it's gonna be 2. Because we're gonna go from the left side. It's different when we go from the right.
It's 3.
Yeah, see that? From the right, we're going to 3. It's getting closer and closer and closer to 3.
This was on our final exam.
So what would B be in this case? If I say my right-handed limit, my right hand,
Positive
What is the
infinity.
limit? Positive
Infinity.
infinity. That's this one going up. That's what asymptote is. It goes up forever, and you can't find when it's gonna
No, we
hit
did
this
this.
line.
Yep.
Practically
Oh,
never,
Not equation.
right? If I go from the left, it's just the reverse.
Negative.
It's just going down to negative
Negative.
infinity.
Like we just realized x is 2.
Okay. So one-sided limits can be
Or like
defined,
when x is
Yeah,
y.
when x is
but
2.
regular limits without the plus and the minus, that's where it's different. So once there's a break, we'll talk more about that I think next week. Once there's a break, there cannot be a limit. In general. Okay, I'm gonna redefine some things later on. Let's go through some examples. Just make sure that we got the idea of how to read limits from a graph. So here's a function, piecewise function, and we want to target this. All these limits are limit as x is approaching -2. Because I know it's a little harder to see. -2 is over here. This x value is -2. So from the left, what is it going to hit?
-1.
Yeah, from the left, it's going to go to -1. You see, it's going to get close to, but we're not going to count it at that point. Right? So, up from the right.
-1.
Yeah, from the right is also -1. Does that make sense? What about limit as x approaches -2?
5. Yeah. Is it 5?
No.
I can't even read the question.
No, it's not 5.
Still -2.
Still no.
Interesting.
We follow the function of where the line of the function goes. We don't follow where the dots go. That's the difference between a limit and a function, well, checking a function. However, f of -2 will be 5. The function evaluation follows the dot. The limit needs to follow the line at all times. Okay, so that's an example here. Any questions so far? Let's take a look at another example. So there's a bunch of examples here,
It's the third one.
here and there.
You want to what? x2
Same
As
graph.
x approaches 0 from the left.
We're gonna have x is approaching 0. Okay? So I want you guys to think about, write this down on the side for yourself, talk to your neighbors if you need to. Take about 30 seconds. I wanna know what the limit is, approaching from the 0 from the left, right, on 0, and what is f of 0.
Aren't they all just 0?
Take 30 seconds.
Wait, Jonathan, assuming that that point is 0, then it's all just a 0,
Yeah.
right?
Wait.
But let me think about it.
As x approaches 0 from the left, that graph looks like it hits 0, right?
It hit 0.
Yeah. And as it approaches from the right, 0.
It still hit.
And then the limit itself is 0.
Wait, but
And then the function of
when
0
it's coming from the right, it
is
hit 0 at 2 different points.
the what?
It hit 0 at 2 different points when it's coming from the left. I mean the right.
It can 0 can only be 1 point.
Then
It
which one is
approaches-
Because it hits 7 and it also.
Okay, you guys ready for the answer? Okay.
Oh.
Oh.
All 0.
Oh.
Yeah. Okay. So yeah,
All
all
0.
0.
All 0.
Oh wait,
Just
what?
to validate and
It is
verify
zero.
your thinking.
What about that point?
Right?
No, the hook where
No, it's
no
on the right.
where
down. Yeah.
0, yeah.
What about it?
He was confusing
Does
us
it-
over that.
Oh,
If it's
what,
coming from the right,
what if the
doesn't-
limit was approaching this?
Yeah.
Still all zeros.
Huh.
Because we're following where
No,
the
it's
graph
because
goes.
x equals 0. That's x
Right.
equals 7.
Oh.
We don't
yeah,
really care
yeah.
about
My bad.
what else the graph looks like, whether it's a function or not. But actually, it should be a function. But this is the one where we're looking at when that goes to 0 there. So it's all zeros in that case. So when it's continuous, so you see how when we're focusing on x approaching 0, I don't care what happens here. I don't care what happens here. I only care about what happens within this zone here, as closely as possible. So limits is where you tunnel vision and focus on this section. Anything else is negligent. We don't need to worry about it. Let's go to another example. Funny how one graph can generate all these questions. I want to approach 2 now. 2 is over
2
here.
from the left, 2 from the right.
I want to
and
approach 2 from the left, right, both sides, and the function evaluation.
Okay, so it's 1, 2,
Again,
undefined, or no limit, and then 2. Because remember that example? The first example? Where the limit
Yeah.
itself can't be there. Because either it approaches from the left or the right, so there's no limit.
So what f of 2?
It's just where the point is. It's 3 or 2.
Wait, so it's
One,
one
two.
undefined.
Wait, can you press slideshow so it's bigger?
He doesn't want to full screen it.
Last time I did slideshow, it froze my Mac.
Well, we're all blind back here.
I know,
So.
I'm sorry.
Do you know how to zoom in on your computer?
Okay, that works.
No.
Oh wait, maybe that doesn't work.
It's on the minus one.
Nope, it's not doing it.
There you go.
Oh, really? I'm doing minus.
Oh.
Well, that works well, actually.
Yeah, I was doing minus and it was zooming in.
And then if you press F11, it might go full screen.
Yeah, we're not gonna freeze my MacBook again. I can throw a
Press
MacBook
Alt
out.
F4 stops it from freezing.
Okay, alright. How blinding.
Can you see it better now?
Alright, limit approaches 2 from the left. What is it?
1,
1.
1. Yes, it's 1. How about from the right?
2,
2. How about both sides?
no limit,
No limit.
Limit.
F of 2.
2.
Yep. That's it. So that's a general idea of a limit in terms of like graphs of like how they
Dude, it
move,
feels
where they
so
go,
smart.
and stuff like that. Okay.
This is such a weird feeling.
So if you need to do like side notes of like when your graphs break,
Seriously.
there's no
Just do-
both-sided limits, right? There's no regular limit, but there are one-sided limits. Even if it's not defined, we can still get a limit, as you guys can tell. Okay. So the next one. Another one. I just want to make sure that
So it's
real.
2 undefined.
I want to approach
Yeah.
5 now. 5 is located over here, in case you're having trouble seeing. This is where
Oh.
5 is located.
That's easy. It's all just 2. Or no, wait.
No, they're not all
2,
2.
2, 2, and then none. It's 2, 2, 2, and then undefined.
Yeah. 2, 2, 2 undefined.
Okay, so let's reveal. All the limits are 2. All the limits are 2. Okay, so both the one side. So whether you go to the left or right, you're still getting the same point. It's like when you guys call your friends and you guys want to meet at McDonald's. You're coming from different directions, but you're still meeting at the same point. You're all still approaching the same location, right? So it doesn't matter whether from left to right, you're going to the same place. However, when we go our different ways, that's a different story. So all the limits hit 2. Okay, or getting closer to. The function, however, is undefined. It does not exist. So you guys see how all these examples, I'm really trying to like push in and emphasize the importance of we're getting close to, so we don't care if the function is actually definable or not. Because we want to get as close as possible is the goal. Okay. And that's the general gist. Let's take another example. Continue on. Alright. The one you guys were looking at earlier, the hook. I want to know both sided limits for x is approaching 7. Where you're going from left, right, 7, and function, what the function is.
Zero, zero,
I think,
zero,
yeah, it's
zero.
all
Yeah,
just-
all zero.
Do you agree? All 0?
Yeah. One and false
So-
were wrong.
Yeah, it's all 0. Your function is defined, which is nice. Both sides go to 0, each side go to 0, so everything is 0 in this case. Okay? So one thing about limits is that limits typically, you could go to a spot that's definable. You go to any spot of a graph that's definable, it's okay. Now what makes limits interesting is when you go to positions that are not definable. What happens?
No limit.
Okay, a lot of calculus you're going to see later is that we want to get as close as we can. That's the whole idea of calculus. It's why limits are the foundation of everything in the calculus world. Okay, you can't have calculus without limits. Let's do a check-in. What's the limit as x approaches 2 for this one? 2 is, of course, the interesting part right here.
Undefined. No
Undefined.
limit.
Undefined. Okay. So there's another thing here that I'm going to just state right now as well. So typically, a lot of people throw out the word. I mean, some people may not be super picky, but I somewhat am. For limit definitions, we're gonna say D and E for does not exist. Because limits either exist or they don't. They're never undefined. You see how, if I go from the left-handed side, you have a limit, right? Which means we can actually define it as in some kind of way. So it's not that it's undefinable, it's that it does not exist. Okay, so we're gonna talk about existence in regards to limits. Limited existence. Questions? Complications? As we continue along, let's look at one of the old cases that we saw on one of the slides. Your limit is going to 1 from the left, right, both sides, and the function definition. There is a dot here. Okay, it's an FY, that is a dot, intended dot for you.
Wait, what? I've never seen that before.
Okay, follows the line. So.
Yeah. No. One from the left, it's positive infinity. One from the right, negative infinity. Does not exist, and negative 1 is 1.
Okay. Oh, I see. Get close to.
Because remember, he said the limit has to follow the line.
Yeah.
Wait, infinity, negative infinity
Does not exist.
does not exist.
Going from the
Another one.
left, what is it going to?
Infinity.
Infinity. What's it going to if it's coming from the right?
Negative infinity.
Negative infinity, and how about when it is at negative 1?
Does not exist.
Does not exist, and how about function definition at negative 1?
1.
Yeah. Okay. Now, here's the tricky part on another thing in notation wise. You guys told me that when the limit as x approaches negative 1 from the left, it's going to be infinity, right?
Mm-hmm.
Okay. You can say infinity. You will still get it correct. I do have to say this part because college professors typically don't agree to this, and they all use different one or the other. It's okay to say the answer is infinity. You won't get docked for that, even on the AP test. Or you can say does not exist. Because infinity is not a number,
Oh.
so it doesn't exist. Have you guys ever? Has anyone ever, like as kids, where you guys were like, my number's bigger, I have infinity plus 1, and someone's like, well,
Yeah.
infinity plus 5, I have infinity plus 5.01, mine's bigger. Well, the reality is that infinities are a concept. This is going to sound really weird. One infinity can theoretically be bigger than another infinity. Theoretically speaking, because it's a concept. You don't know how big these infinities truly are. So conceptually, it's just really big. So basically, infinity can be bigger than infinity plus 1. Because you don't know which infinity is bigger. It's a concept. So when your answer spits out this infinity or negative infinity, you can use those as your answers. That's fine. But you can also say, does not exist. Because you're not given a real number. Make sense?
Which one do you want?
I don't care.
Do you have a preference?
I have to say it because of professors in the future.
I'm just gonna use infinity.
But if you use infinity, it's nice. So I would say that, okay, for my preference, I like the infinity statements. Okay? Because does not exist doesn't really tell me exactly what I want, but it's okay to put that because it's still logically true. A lot of professors that I've learned, kind of talked to, they prefer the infinity because infinity tells you if something has an asymptote or not. For example, if I had the graph earlier, right, this limit does not exist. That's not infinity. Nowhere is it going infinity from the left or right. Right? So if I have my answer does not exist, it doesn't clarify whether it's this case or this case. You see what I mean? So typically the infinity is the way to go, but you can also say does not exist.
So if you're in a hunch, if you're in a bad spot, use does not exist.
Yes. If you're panicking and you're like, shoot, I don't know which one to choose, it doesn't matter. At the end of the day, it does not exist. But if you want to go like very specific, again, the infinities tell me the difference between what situation I'm talking about, right? Versus otherwise. Yeah, it gets very technical once you're in like the cap area and stuff like that. So that's what this slide basically means. A limit approaching infinity can be considered as does not exist. Okay, DNE is typically what we're going to use. Okay. Now, if you had a division by 0, like 1 over 0, that is undefined because mathematically speaking, you cannot define it. And yes, mathematicians try. They really try, but they cannot define it. So we say undefined for that case. Okay. Any questions so far? Okay, so the notation-wise is practically the same thing as these. It's just the R changes to like infinity. That's all it is. You just use the infinity symbol, or if you use the DNU, doesn't matter. I hope you guys have calculators by now, so we can take a look at these examples to graph and see what the limit is approaching you closer to. So in your calculus, when you make a graph, think of the, just really think of the tracing feature as the bead you're moving from the left to the or the right, to go to that spot.
Oh shoot.
So let's do an easy one first.
Function there.
And if you guys can't see, I'll write it out loud in my calculator. Okay, give me a moment.
As
So
x
in case you guys
approaches
can't see,
2.
I want you to look at what happens when we have the limit. As x approaches 2 for x squared, what is this? Okay. Do you have a game in the future yourself, or you want to borrow?
How does it work when, is it possible to press like, oh, value x, yeah, x equals 2,
How'd you find limit?
y is 4. No, you just look at the graph.
Oh, I see.